As indicated here, to use a screw for the lag technique, 3 conditions need to be fulfilled. 1. The screw must not purchase in the near fragment, and so a gliding hole must be drilled in the near cortex. 2. The thread of the screw must purchase in the far fragment. 3. There must be a screw head to arrest screw progression. The screw can be a fully threaded cortical screw or a partially threaded cortical shaft screw. In the standard lag technique, the gliding hole is drilled first from outside in, using a drill equal to the outside thread diameter of the screw. In certain circumstances, in order to position the gliding hole optimally in the fracture plane, the gliding hole may need to be drilled from inside outwards, using a drill equal to the outside thread diameter of the screw. This requires very careful rotation of the fragment to reach its endosteal surface. The biology of the fragment should not in any way be compromised by this manoeuvre. Very rarely, if there is a narrow spike at the tip of the far fragment, which would be difficult to drill optimally through a sleeve in the gliding hole after reduction, a technique can be used whereby the pilot hole in the far fragment is drilled first from inside out. The post of a specially curved drill guide is then engaged in the pilot hole and the fracture reduced. With gentle traction on the curved drill guide, the 4.5 drill sleeve is introduced through the sleeve of the curved guide, and the gliding hole drilled through the 4.5 sleeve coaxially with the pilot hole. This requires great skill and experience, but is rarely necessary. Following the drilling of the gliding hole, diagram 1, anatomical reduction of the fracture, and then drilling the pilot hole, diagram 2, the near cortex is countersunk, diagram 3. The use of the depth gauge is critical for oblique screw tracks. It is tempting to hook the guide on the acute angle of the far hole, but, as illustrated here, this will give a screw length measurement that will be too short. It is the obtuse angle that must be engaged. If this proves impossible, then hook onto the acute angled side of the screw hole and then add 2 or 4 millimeters depending on the obliquity. Following depth measurement, the correct length of screw is chosen. The final step is to tap the far cortex. This is a precision maneuver, and the use of the tap requires great skill and surgical discipline. The tap must never be used in a power tool. The tap should only ever be used through a tap sleeve. Not only does this protect the soft tissues, but it controls the alignment of the tap. The tap can cut a thread as it is withdrawn as well as when inserted. Therefore, if the tap is slightly angled as it is withdrawn, it will cut a second female helix and damage the thread that it cut on insertion. This can compromise the screw hold. Such a double helix is avoided by controlling the axis of the tap carefully, using the tap sleeve as the tap is gently unscrewed from the pilot hole. If a screw is inserted by the lag technique perpendicular to the long axis of the bone, it produces maximum resistance to any shear forces generated by axial loading. On the other hand, if the screw is inserted perpendicular to the fracture plane, it produces maximum interfragmentary compression. These competing objectives can be managed in one of 2 ways. Firstly, 2 screws can be inserted, one perpendicular to the bone's long axis and the other perpendicular to the fracture plane. The other option is to produce maximal desirable interfragmentary compression with 1 or more screws perpendicular to the fracture plane, and then achieve resistance to shear by using a plate to protect the primary screw fixation, the so-called protection or neutralization function of the plate. It is clearly important that the holes in the near and far cortices be coaxial. If the holes are not coaxial, as the screw engages both fragments, the reduction of the fragments will be affected. For similar reasons, an interfragmentary screw should pass perpendicular to the fracture plane, with the holes in the center of each fragment in a transverse section. So far, we've concentrated largely on cortical screws, which are designed to gain thread purchase in hard cortical bone. Cancellous screws are designed to be used where the screw thread must gain a hold in cancellous bone. The cancellous screws have a deeper thread and a coarser pitch than their cortical counterparts. In addition, the tip is of a different design for reasons to be explained. Note that the spiral of the helix increases from a point at the tip to the full thread diameter over 2 complete turns. Those cancellous screws that are not fully threaded have a smooth shaft. The head design is similar to that of the equivalent cortical screw. Cancellous screws create their own thread not by removing bone, but by impacting it aside, rather as a snow plough creates a path through the snow. The tip design achieves this. The standard large cancellous screw has a 3.1 mm core, but the unthreaded shaft has a diameter of 4.5 mm. The outside thread or nominal diameter is 6.5 mm. Therefore it is referred to as a 6.5 cancellous screw. The drill bit used for the pilot hole is 3.2 mm in diameter. The small cancellous screw has a 1.9 mm core, so a 2 mm drill bit is used for the pilot hole. The unthreaded shaft is 2.4 mm in diameter. The outside thread diameter is 3.5 mm, hence the 3.5 cancellous screw. This replaced the former 4 mm cancellous screw. Cancellous screws may be fully threaded for use in attaching plates to intact metaphyseal areas, or partially threaded for using as lag screws through a fracture plane. The 6.5 cancellous partially threaded screws have either a 16 mm or a 32 mm threaded length. The small cancellous screws also have a fully threaded version or a partial thread, the length of which is proportional to the overall screw length. Let us take a distal femoral unicondylar fracture, such as this 3-3-B1 fracture, as a model to demonstrate points of technique of inserting one or more 6.5 cancellous lag screws. The fracture is first reduced and held provisionally with one or more Kirschner wires. A 3.2 mm pilot hole is then drilled across the fracture plane and its depth measured. A 6.5 cancellous tap is used only to open the thin metaphyseal cortex and the immediately underlying cancellous bone. The screw of chosen overall length and thread length is then inserted. If the cortex is anything other than strong, then a washer is used. If in doubt, use a washer. As the screw is driven home, the tip creates the thread in the bone by impacting it aside. There is no need to drill the cortex to 4.5 mm to accommodate the shaft. This will enter the bone with ease once the 6.5 mm thread has been created. As the screw is tightened, the fracture plane is compressed. Cannulated cancellous screws are available and can be used, a guide wire being inserted instead of one of the Kirschner wires, at the stage of temporary stabilization after reduction. In conclusion, this guide has hopefully made you comfortable with the essential attributes of the commonly used surgical screws and the techniques for their insertion. This will equip you with a basic understanding of the use of one of the most fundamental surgical tools.